Here we have another pretty straightforward example, and I will switch this one up a little bit because the numbers should be a little bit more comfortable for people. So I would like to show how to do this instead of solving by taking square roots. Let's look at it by factoring, and let's also look at it with the quadratic formula, which I think both of these methods are the more inconvenient ways to do a problem like this. And if you've already done it, you probably did it by taking square roots. I just want to show you what it would look like. So let's get into it. If we were to try to factor something like this we have a quadratic binomial. We are more familiar with an example, perhaps like x squared minus 36, right? I'm just going to look at the expression, not an equation at this moment. X squared minus 36 is what we call a difference of two squares, in this case, two perfect squares. We like to look at this and decide, well, what's being squared in both of our scenarios? And I like to refer to these as putting on our glasses, right? We're looking right through and seeing, okay, well, we're squaring x to make this, 6 to make this. So in a difference of two squares situation, we end up with x minus 6, x plus 6. This is sort of a shortcut to doing this, which we can reason through when we think about distribution using the mnemonic device FOIL, first times first, outer, inner, last times last. And we'll see that the outer and the inner will cancel out or become 0 because you'll have a positive 6x and a negative 6x, because these two factors are what we call conjugates. That means that they start off the same way, and we just kind of switch up that ending in a distinct way, which is the plus 6 and the minus 6. So one has a plus, one has a minus, only that middle sign. They're not opposites. The opposite of x plus 6 is actually negative x minus 6, right? So think of that in that way. The opposite of x minus 6 is negative x plus 6, okay? Now, if we had, instead of this expression, which would maybe have directions such as factor, if we had an equation, the directions may be find all solutions or solve. So you would take each of those factors, set them each equal to 0 by the zero product property, and we would get two distinct answers, 6 and negative 6. Great. Well, how can we factor this if the rule for this situation is difference of two squares? And I'm going to try to show, we'll see how long this video gets, but how to do that using even AC method and grouping, but one thing at a time. Well, plus, how can we change this up so that plus 36 no longer says exactly plus 36? It will still mean plus 36, but how could we show it using a minus so that we have a difference so that we can roll into that difference of two squares approach? Well, plus is the same as minus a negative. Now, let's roll into that same approach. What's being squared to make each of these pieces of our equation? Well, x is being squared to make x squared, or the square root of x squared is x. Same concept, right? Well, what is being squared to make 36, or I'm sorry, negative 36, or what is the square root of negative 36? This would be 6i. Okay, so we can set up those conjugates, x plus 6i and x minus 6i equals 0. And then all we need to do is, still moving forward, apply the zero product property. So we set each factor, each part of the product equal to 0. I constantly stress that it's called the zero product property because it doesn't always do the job. But the other day, for instance, I just watched someone take something that wasn't factorable, a quadratic trinomial, and bring over the constant and then factor out an x and set the x and then the other little linear factor equal to that number. No. We had a very long conversation about this, okay? You cannot do that. This is a special situation that if you have a product, you could say both or all three or all four, all the pieces of the product can be equal to 0. You can't do that with another number, right? So moving forward, here we'll get x equals the negative 6i and x equals positive 6i. When I write answers that I get from factoring, typically I just sort of leave them each underneath their factor. Usually when I'm using this type of approach, it's maybe going to lead to me graphing, or in the future, maybe testing intervals. In calculus, we kind of use this approach and we find something called critical numbers. And then we test or determine if a graph or function is maybe increasing or decreasing between those values. Or maybe we figure out if the graph is concave up or concave down between those numbers. So by stacking them with this plus minus in front for the answer, x equals plus minus 6i, granted we wouldn't use imaginary numbers for that, just in general, it's not as nice to lay them all out on a number line, but we'll cross each bridge as we get to it. So this is us solving an equation where we got imaginary answers in our solutions, but we did so by factoring, right? Using a factoring approach. Now, I said I would also try to do quadratic formula for this, so if I could do this in under a minute, I'm going to make this happen. So x equals negative b plus minus the square root of b squared minus 4ac all over 2a. And I looked at some notebooks today, and those quadratic formulas were ugly. That roof was not covering everybody. This line was not a good foundation for our numerator. Not good. Now, we're looking at this equation. What, can I fit it above? I think so. If we think of our quadratic being ax squared plus bx plus c, and we're dealing with x squared plus 36, well, what are my a, b, and c values, right? A in this example is 1. B is 0. C is 36. So it's a little weird when b is 0, which is kind of why using the quadratic formula is kind of silly. But let's see what happens, right? X equals negative b. I'm being a little ridiculous, but here we go. Obviously, you don't have to write anything. The square root of plus minus the square root of b squared minus 4ac all over 2 times 1. Okay. Now, this doesn't matter, right? X equals plus minus the square root of. That also doesn't matter. Negative 4 times 1, the multiplicative identity, times 36. A perfect square times another perfect square will always give you another perfect square. If you keep multiplying perfect squares together, you will get another perfect square. Think about how that number's built, right? Because here we'll have the negative, or negative 1. That 4 is really 2 times 2. And the 36 is 6 times 6. Could I do 2, 2, 3, 3? Sure. But you could also stop early. You could stop at 6 and 6. It's just as good. All over 2 times 1, which is 2. Now, I hate when I do this, but here we are. The negative can come out as I. Takes a pair to make a square. 2 can come out. A 6 can come out. And that's going to become I. So what do we have? X is equal to plus minus 2 times 6 times I, nothing left inside my radical, all over 2. We can reduce or simplify those 2's, because 2 over 2 is 1, and that's it. Plus minus 6i. Same answers, this time they just kind of come stacked, consolidated into a little package. If I actually followed through and multiplied 4 times 36, well, I would have gotten 144, and the square root of 144 is 12, and 12 over 2 is still 6. So lots of ways to get the right answer. Just be careful, don't break any rules, and don't be careless. Double check, triple check, compare, and make sure you're doing it correctly. That's all. Don't just assume it's perfect. Check, compare, phone a friend, do what you got to do. All right. So hopefully this approach was a little bit enlightening. If you thought it was wasting your time, put a thumbs down on the video, and you can check out what's next on the screen or go to the playlist. Adios.